One of the most common problems encountered in high school algebra is the question of finding the zeros of a polynomial in a single variable. Viewed from a geometric lens, this is the same as finding where the graph of that polynomial intersects the x-axis. It doesn't take long to notice after graphing a few examples that a polynomial of degree n can have at most n zeros. However, it seems that the exact number of zeros would depend greatly on the individual polynomial. For example, a parabola could touch the x-axis in 2 points, or it could be tangent to the axis at a single point, or it could fail to intersect the x-axis at all, depending on the coefficients of the quadratic equation that describes it. As it turns out, though, a famous result called the fundamental theorem of algebra states that if we expand our number system to the complex numbers, which contain square roots of negative numbers, and also allow ourselves to count the same point multiple times when the corresponding factor appears multiple times in the polynomial, then a polynomial of degree n has exactly n zeros. No more, no less. This simple problem is actually an introduction to a branch of mathematics called algebraic geometry, in which we explore the deep and fundamental relationship between the realm of symbols and the realm of shapes. We often represent algebraic equations as geometrical objects, such as curves and surfaces, which we call varieties, and then look at solutions to those equations as points on those objects. The insights we find highlight connections to such diverse areas of mathematics as topology, differential geometry, complex analysis, number theory, abstract algebra, and more. As before, we often consider complex numbers and multiple intersections, but we also find it useful to consider another very important number, infinity. If it seems strange at first to use infinity as part of our geometry, allow me to offer a change in perspective, so to speak. Consider this very simple question. Are these two lines parallel? Well, of course not. They intersect right here, so how could they possibly be parallel? But what if I do this? Now you know something is going on, because while you can clearly see those two lines intersecting, you know that if you were to step into the world of this picture, you could look straight down below you and see that the lines are perfectly parallel. The point where the two lines intersect in our picture is usually called a vanishing point in art. Mathematicians call it by a different name. They call it a point at infinity, since in order to get to that point, you would need to go infinitely far into the distance toward the horizon. The introduction of points at infinity into mathematics comes from the study of projective geometry, which was originally developed to answer the question of how to faithfully represent objects in perspective in art. The rules of projective geometry are somewhat more relaxed than our usual Euclidean geometry, because we temporarily remove the concept of distance. When distance is no longer an issue, suddenly being infinite is no longer that big of a deal, and points at infinity gain the same status as any other points. As a result, we can make powerful statements like, any two distinct lines intersect at exactly one point. In Euclidean geometry, we would have needed to make an exception for parallel lines, but in projective geometry, parallel lines intersect at infinity. Of course, if we no longer have distance, we can no longer talk about concepts such as congruence, or even similarity. Instead, we have to see what properties are preserved via projective transformations. However, once we've come to understand what relationships are preserved in our relaxed projective space, we can come back to Euclidean space and see what happens when distance is reintroduced. It turns out that the most important thing in this case is the concept of the cross ratio. Given 4 collinear points A, B, C, and D, their cross ratio is defined as the ratio AC times BD divided by AD times BC. Here, we're assuming that the line has an orientation, so that there's a positive direction and a negative direction. For example, suppose we look at these 4 collinear points, A at 0, 0, B at -2, 0, C at -1, 0, and D at 3, 0 in that order. We'll also assume that the rightward direction is considered positive. Then our cross ratio is calculated as AC, which is -1, times BD, which is 5, divided by the product of AD, which is 3, and BC, which is 1, giving us a result of -5/3. The cross ratio is special because it's invariant under any perspectivity, which for our purposes is a special kind of projective transformation in which a set of points on one line is mapped through a certain point, the center of perspective, to a set of corresponding points on another line. To see what I mean, let's take our 4 points from earlier and project them onto the vertical line x equals 1, using 2, 2 as our center of perspectivity. Then the images of our points are a prime at 1, 1, b prime at 1, 3/2, c prime at 1, 4/3, and d prime at 1, 4. Then, if we assign an orientation to the line and calculate the cross ratio using this new set of points, maintaining the same order, we end up with the exact same result as before, -5/3. Thus, the cross ratio has been preserved. There is one special case we need to take into consideration, though. What happens if one of our points is all the way at infinity? What do we do with the infinite distances? Well, intuitively, if our point were some very large finite distance from the other 2 points it's being compared with, then the ratio of its distances to the 2 points would be very close to 1. So in the case of a point at infinity, we simply say that the ratio between those 2 distances is 1, and we cancel out those parts of the formula. Now there's a very interesting situation that sometimes comes up when we calculate the cross ratio. If, for a given set of 4 collinear points, the cross ratio comes out to -1, we say that the set of points is a harmonic set. In particular, we call the point D the harmonic conjugate of C with respect to A and B. One of the simplest examples is when 3 points are evenly spaced along a line, in which case the harmonic conjugate of the center point is the point at infinity. All it takes is a quick calculation of the cross ratio, canceling out the terms involving infinity, to show that the cross ratio is -1 and that therefore A, B, C, and D form a harmonic set. This is a significant discovery because it means that if we want to draw a perspective representation of the plane, then the appropriate way to foreshorten a sequence of evenly spaced points on a line, that is to make them get closer together as we go further off into the distance, is to ensure that any 3 of the points in a row form a harmonic set with the corresponding point at infinity. We call such a sequence of points a harmonic sequence. Armed with our knowledge of harmonic sequences, we can construct a realistic-looking perspective grid as follows. First, choose a line and mark off evenly spaced points on that line. Then, some distance upward, draw a parallel line, which will be the horizon, which is called the line at infinity in projective geometry. Choose a point on this horizon, which will be a point at infinity, and draw lines to it from each of the evenly spaced points. Finally, choose one more point along one of the lines that will count as 1 unit of length in the direction of the horizon. From here, the picture basically draws itself. Keep in mind that in a square grid, not only will the actual lines of the grid be parallel, but so will the diagonals of the squares. Therefore, if we draw one of these diagonals and look at where that diagonal intersects the line at infinity, all of the diagonals should intersect at that same point at infinity. From there, by looking at where these diagonals intersect our original set of lines, we can see where the rest of the grid lines should go. Now that we have a grid, it seems only natural to try graphing things on it. It's no surprise that straight lines will still be just straight lines. But interesting things start happening when we graph curves. Suppose we graph the curve y equals x squared. Should be a parabola, right? But watch what happens as we plot points. As we go further out on our parabola, it actually starts to curve in on itself. In fact, if we connect the dots, we get a different conic section, an ellipse. Viewed from a projective lens, a parabola is nothing but an ellipse that's been stretched out so far that one end is all the way at infinity. And if we stretch that ellipse even further, we would get a hyperbola. So you might be wondering, where does the other end of the ellipse go? What lies past infinity? We'll see in just a bit. Now let's go back to our parabola. Just where does our parabola intersect the line at infinity? Can we even find a meaningful way to describe such a point numerically? It turns out that we can, if we introduce what are called homogeneous coordinates. To see how that would work, first let's consider how we would put homogeneous coordinates on a line. We need to embed our one-dimensional line into a two-dimensional plane, so we'll place it at y equals 1. Now every point on the line can be paired with a line through the origin. If the point is a1, then the equation of the line is x equals ay. This gives us a one-to-one correspondence between the set of all points on the line, called a range of points, and the set of all lines through the origin, called a pencil of lines. Well, almost. There's actually one line that can't be reached this way, the horizontal line y equals 0. However, we can notice that as the point of intersection goes out toward infinity in either direction, the line through the origin certainly looks more and more horizontal. This suggests that we can let the horizontal line through the origin correspond to the point at infinity. Yes, the point. It's important to understand that this is a single point in infinity. Unlike the usual extended real line, where we have two infinities, one positive, one negative, the so-called projectively extended real line only has a single point at infinity, formed by effectively joining positive and negative infinity together. What results is an unsigned infinity, neither positive nor negative, much like 0. Going back to our correspondence between points and lines, look at the line that goes through our sample point A1. If we scale the x and y coordinates by the same number, say k, what we get is still a point on the line. In particular, notice that the ratio between the x and y coordinates is left invariant as long as we're on this line. We could project our point onto any other horizontal line, except the one at the origin, and we would still have a one-to-one correspondence between points on the line and lines through the origin. For this reason, we'll use the notation x:y to refer to points on the line, with the understanding that for any non-zero value of k, the points xy and kx,ky really represent the same point, because they're connected to the same line through the origin. This is in fact why we call these homogeneous coordinates. Now what about the point at infinity? Well, remember that the point at infinity corresponds with the line y equals 0, all of whose points have, unsurprisingly, a y coordinate of 0. So we'll use x0 to represent the point at infinity. This agrees with our intuition that dividing a non-zero number by 0 really should give an answer of unsigned infinity when we're working in the projectively extended real line. The only coordinates that we consider invalid are 0, 0, since the origin is on every line in our original pencil, and thus can't be used to describe any one line. This also makes sense if you remember that in calculus, 0 divided by 0 is an indeterminate form, and can represent any number. All in all, the space we've modeled is known as the real projective line. We can follow a similar process to put homogeneous coordinates on a plane. This time we'll embed our two-dimensional plane into three-dimensional space, so we'll place it at z equals 1. Every point on the plane can be paired with a line through the origin. This time, if we scale the x, y, and z coordinates by the same amount, we'll stay on the same line through the origin. So we'll write our homogeneous coordinates as x:y:z, with the understanding that if we scale all three coordinates by the same amount, we're really looking at the same point. Now, as before, almost every line through the origin will correspond with a point on the plane. This time, however, there are infinitely many exceptions. Any horizontal line through the origin will not intersect our plane. However, if we look at a vertical slice of our situation, we can reduce it to a problem we've already seen before. Let each horizontal line correspond to a different point at infinity. These points at infinity will be of the form x, y, 0, which can be thought of as the point at infinity in the direction of x, y. Of course, it's important to know that this is the same as the point in the direction of negative x, negative y, since this is just scaling by -1, and we know that the two directions are really connected. If we connect all the points at infinity together, then we have the line at infinity, just like the horizon we saw earlier. And as before, the only invalid coordinates are 0, 0, 0. By including our points at infinity, we have extended the Euclidean plane to what we call the real projective plane. Now that we have a numerical way to represent points at infinity, Let's see where our parabola y equals x squared intersects the line at infinity. Our first step is to homogenize the polynomial equation by multiplying each term by just enough z's so that every term in the equation has the same degree. In this case, 2, so we end up with yz equals x squared. Notice that if we set z equal to 1, we recover the original equation of the parabola. More amazingly, if we scale x, y, and z by some constant k, we can factor out and cancel the k's to just get the original equation back, which shows why our process plays so well with homogeneous coordinates. Now remember that a point at infinity can be represented with a homogeneous z-coordinate of 0. So to find out where our parabola reaches infinity, we just need to set z equals 0 in our equation, in this case giving us y times 0 equals x squared. Finally, we need to figure out which values of x and y will make the equation work. In this case, x would have to be 0, while y could be anything. Thus, the parabola reaches infinity at the point with homogeneous coordinates 0, y, 0. Since we can scale these coordinates by any number, we can divide through by y to get the coordinates 0, 1, 0, which we can intuitively think of as the point at infinity in the direction of 0, 1. This agrees with our picture from earlier, which showed that the parabola closed off at the end of the y-axis. Similarly, with the hyperbola, we can find that it intersects the line at infinity in 2 different points. What's more, now we know where the other end of the ellipse went to form that hyperbola. Since a point at infinity connects the positive and negative ends of a number line, the ellipse wrapped around infinity to the other side, which is why the hyperbola actually has 2 branches. Let's look at another example. Consider the unit circle, whose equation is x squared plus y squared equals 1. Where does it intersect the line at infinity? Well, it doesn't, you might say, at first. But let's double check just in case. First, we'll homogenize the equation, giving us x squared plus y squared equals z squared. Then, we'll set z equal to 0 to find where the circle hits infinity. So our equation becomes x squared plus y squared equals 0. It might seem at first that the only solution would be for x and y to both be 0, but this would give us the invalid triple 0, 0, 0. But there's another possibility. If we rearrange the equation to y squared equals negative x squared, and then square root both sides, we can see that there are 2 complex solutions, y equals ix and y equals negative ix. Thus we have 2 solutions in homogeneous coordinates, x ix 0 and x negative ix 0. Scaling these back by x, we arrive at the points 1 I 0 and 1 negative I 0. By expanding our number system even further to the complex projective plane, we've found 2 points where a seemingly innocent circle blows up to infinity by allowing it to go off in the imaginary direction. These observations we've made hint at a much deeper principle at work. In fact, a generalization of the fundamental theorem of algebra, as we discussed at the beginning of this video. This principle is known as Bézout's theorem in algebraic geometry. Bézout's theorem states that if 2 algebraic curves in the plane, that is, curves described by polynomial equations, meet in finitely many points, and if they have degrees m and n, then the number of intersection points is at most m times n. But even more amazingly, if we consider complex coefficients, multiplicities of intersections, and points at infinity, the number of points of intersection comes out to exactly m times n. The fundamental theorem of algebra can now be viewed as a special case of Bézout's theorem, where we're looking for the intersection of a polynomial curve of degree n with the line y equals 0, which as an algebraic curve has a degree of 1. But this also means that, for example, every conic section intersects the line at infinity twice, since a conic has degree 2, and even the line at infinity has degree 1. This is easy to see for a hyperbola, while for a parabola, we can call the point of tangency a double intersection. And for an ellipse, we'll get 2 intersections involving imaginary numbers. By the same token, any 2 conics would intersect in exactly 4 points, Easily visible with well-chosen conics, but still true even in not as obvious cases, thanks to the inclusion of special types of points. A modern application of Bézout's theorem is in the study of elliptic curves, a particular class of third-degree algebraic curves. Elliptic curves were at the front and center of Andrew Wiles' eventual proof to the infamous Fermat's last theorem, and they're the subject of the Birch and Swinnerton-Dyer conjecture, which is one of the 6 remaining million-dollar millennium problems posed by the Clay Mathematics Institute. But such a satisfying and far-reaching result as Bézout's theorem would not have been possible if not for the inclusion of points at infinity and the tools and concepts of projective geometry that help us to understand them.